All right, so this is a topic that I've been wanting to talk about. This is topic number 4, showing that two lines are skew and finding their distance if they are. So there isn't really like a set equation to show that two lines are skew. We're gonna note that the answer to this will be a proof by contradiction. So right there, proof of contradiction, meaning that we have to prove that everything else is wrong to say that this is right, right? That they are skew. So we got to prove two things. We got to prove that they are not parallel and prove that they do not intersect, right? So what's going to be given is two sets of parametric equations corresponding to lines L1 and L2. I wrote some notes here, so it'll probably be helpful to look over these notes first before we watch this video. And I'm gonna send you a PDF for that, so you could go over it if anything else is unclear. Okay, so I'm gonna just read over it real quick. So how do you test if it's parallel, right? Vector 1 and vector 2 are parallel if they are the same or are multiples of each other. Sometimes that's a little bit vague. You can't really see right away. So another easy way to figure it out is to take the ratio of each component. So take the ratio of both x's, take the ratio of both y's, take the ratio of both z's, and see if they are equal to each other. And if they are equal to each other, then they are parallel. And if they're not, then they're not. Okay, so okay, how to test if they're intersecting? And that's if both x's, both y's, and both z's are equal. Then that means the lines do intersect. So we're gonna go over an example right now to make that more clear. All right, so we got an example here. We're given this. Show that if L1 and L2 are skew lines. Okay, so these are given in a parametric, a set of parametric equations, right? So we're going to rewrite those parametric equations as vectors. So you got a vector 1 and a vector 2 corresponding to 1 and 2, right? So your vector 1, that's just corresponding to these values right here, with a t, the coefficient of t, right? So you got a -2, you got a 3, and you got a -1. And same for v2. All right, so I want to do the ratio bit because I guess you could tell here in this case that they're not equivalent to each other. They're not equal and they're not equivalent. So but sometimes when these numbers are different and these numbers are more or bigger or harder to see, you're gonna have to use something like this. So take the ratio of them, meaning that you take this component, make them so you take this component and then this component and then this component and set them all equal to each other, right? And then you could simplify. That's what's good about this. You can simplify so you can see it in smaller numbers. Because -2 is not equal to 1 and these are not equal to 1/2, then they are not parallel. So because we said that they're not parallel, we can move on to find out if they are intersecting or not. Okay, so I just rewrote that. Whatever is given, I rewrote it here. So let's find out if they're intersecting, right? To do that, you set these right equal to each other, not in the same way that we did previously, but you're gonna set the x's equal to each other. So I color coded them for that reason, so you can see exactly what is what. So that's just that, and this is just that, and this is that, and that's just that. Okay, and then there's that, and this is that. All right, and then here I just simplified them. And what we're gonna do is we're gonna take two of these equations. It doesn't matter which two, but we're gonna take two of these, and I just so happen to pick x and y, right? So I took this equation and this equation, and we're gonna solve them simultaneously. We're gonna solve them simultaneously to find t and s. right? So we're just going to do that by, I did a elimination, not elimination, substitution. And then I found that t is equal to 1. And then I plug that back into here. You could plug it into any of these equations, you get the same answer, but I plugged it into here because I haven't used it yet. And then we get s equals to 0. All right, so now that we have t and s, we substitute t and s back to these original equations that we made, right? And we're gonna see that this right here, right, corresponding to that, they are in fact equal. So -1 equal -1. And then same for y and same for z. So because that's the case, then that means the lines do intersect. Okay, that means the lines do intersect at x equals -1, y equals 2, and then z equals 1. Right, so this is the answer if this was the kind of question, right? But I mean, it's the same concept. You're gonna have to do the same exact thing to find if they're skew or not. But the difference in the test is that you're gonna actually find that this wouldn't be intersecting line, because you're trying to prove that they are skew. Okay, so all right, so okay, so if it was a problem that happened to be skew, we're gonna have to find the distance between them. Okay, so this is the second part of this. This is the next part of this topic. And we now recall the formula for distance is the absolute value of d1 minus d2 over the square root of a squared plus b squared plus c squared. And we know that d, right, is equal to ax plus by plus cz. Because what is that? That's something. I know it is, but I can't find it in my head right now. But anyways, we substitute this for d1, and I leave d2 there for now, but we can also substitute this kind of thing for d2, but note it to be ax2 by2 cz2. Okay, oh, I wrote it right here, silly. Okay, right, so we're gonna use this formula, and this is our example right here. So I've already done this example before, and I did do the same exact things that I did previously to find out if they were parallel or intersecting. And so we're gonna find the distance between these skew lines. Okay, so I noted that okay, first of all we're gonna transform these parametric equations into points, right? And so those points are just these right here, right? Because when we're looking for vector, we're taking the coefficients of t. When we're looking for the points, we're taking these independent numbers over there, right? So you got p1, you got 1, you got -3, and then you got 1 again. And that's going to be your x, y, z, or x1, y1, z1, but we don't really have to write that. P2, we do have to make a note that it's x2, y2, z2. Why? Because we're going to use that for solving d2, okay? Because we actually need that value. And we also transform that into vectors. Like I said, you got a 5 here, a 2 here, and and a 1 right there. Okay, and same for L2. And the cross product of these will give me our values for A, B, and C for the equation. So there's going to be that, and that, and these, right? So find the cross product. You find that this is your vector, this is your A, B, and C. And then we're going to use these values and these values and substitute, oh my god, these values, and then substitute them into there. Okay, that looked crazy. But we're going to substitute them into D2 to find D2. You could take a long look at it to analyze it, but So we found D2 to be 65. And all we got to do is substitute that into there. So remember that we're minusing, right? We're subtracting D2. And this, I just substituted the values for here too. But in this part right here, I used these values for P1. So it's just the X, Y, Z. And then this is just A squared, B squared, C squared. And then get this answer. This was actually on the first test, now that I'm really thinking about it. And this was the answer for the first test. So, okay, I hope that was clear. And if it's not, then I'm always here for questions. Hopefully I can help. Okay.